Although it seems like a strange place to start, we're going to begin our unit on electrons with a review of electromagnetic radiation that we will tie into the electron cloud later. So electromagnetic radiation is just waves of energy. We've talked about gamma rays so far with nuclear reactions, but electromagnetic radiation also includes visible light, infrared, microwaves, X-rays, things that you've heard of before. The two things that we need to know and discuss that relate to electromagnetic waves is that they all have a measurable wavelength, which is just how long is the wave, and they also all have a frequency, which is the number of waves that occur during a certain amount of time. Because electromagnetic radiation all moves at the same speed, so it's all going the speed of light, wavelength and frequency are inversely related. So if you look at these three waves right here, okay, let's say they're all starting at point A and moving to point B. Okay, if they have to get from A to B in the same amount of time, then the wavelength is going to affect how many waves exist in that space. So the big waves have a much lower frequency. The medium-sized waves have to have a higher frequency in order to keep up with the big wave. And then the very small waves have to have a really high frequency in order to cover the same amount of space. If you look at the electromagnetic spectrum all in order, you can see how the size of the wave gradually transitions one type of radiation into the other. So over here on this side of the spectrum, we have our largest waves, okay, which have the lowest frequencies. And then all the way on the other side, we have the gamma rays, which we talked about with nuclear. Very, very small waves, which means that they have a very, very high frequency. If we look into the visible spectrum with just a little bit more detail, so these are the parts that we can actually see. Okay, we have red light over here closer to the radio wave side, and we have violet light over here. So that means that red waves have the lowest frequency because they have the largest wavelength of visible light, and violet waves have the highest frequency, which means that they have the smallest wavelength. So, your reference sheet has the electromagnetic spectrum on it. It is a little bit simplified compared to the last picture. So if you look right here, okay, all you have are wavelengths. So if you are asked to interpret the reference sheet in order to figure out frequency, you have to understand how they relate. So if the radio waves have really long wavelengths, then that means that they have very low frequency. Okay, if the gamma rays have the shortest waves, then that means that they have really high frequency. So if we're looking at a question like this, which type of energy has the highest frequency? Okay, here's visible, X-rays are here, and infrared is right here. Okay, so according to the sizes, 10 to the negative 4 is the largest size, 10 to the negative 7 is in the middle, and then these 10 to the negative 10, 10 to the negative 11s mean that that would be the smallest waves. Smallest waves equal highest frequency. So that means that X-ray of these three is going to have the highest frequency. If you're asked to convert between units, you first have to know that this is the equation we're going to use to do that. So since all of the radiation is moving at the same speed, which is the speed of light, 3 times 10 to the 8th, the wavelength and the frequency can be multiplied together in order to reach that speed every single time. So if this number is always the same and you're given one of these numbers, then you can plug one in and solve for the unknown. Our speed of light is meters per second, so that means our wavelengths are going to be in meters, and then the 1/2 portion of this, okay, is a unit called hertz. So if we're solving this question right here, what is the wavelength of a wave with a frequency of 3 times 10 to the 12th hertz? We're going to plug in what we know. So we have speed of light equals wavelength times frequency. Speed of light is always the same number, 3 times 10 to the 8th meters per second. Okay, the wavelength is what we don't know, and frequency is 3 times 10 to the 12th. So in order to solve for wavelength, you would do speed of light divided by 3 times 10 to the 12th. And your answer is 1 times 10 to the negative 4 meters. So, if we are solving for wavelength, then we could be asked an additional question. What type of radiation is it? Okay, here's your magnitude of the size of the wave right here. If you go back to your reference sheet and you look at this, let me just clear this out of the way. Okay, we can look here and see all of the different magnitudes. 10 to the negative 4 is right there. So that means our answer to the second part of this is that this is an infrared wave. If we want to identify the type of radiation that consists of waves with a frequency of 3 times 10 to the 19th, we're going to use the same equation as before. So speed of light, 3.0 times 10 to the 8th meters per second. Okay, the frequency is, or the wavelength's what we don't know, and the frequency is 3 times 10 to the 19th hertz. Okay, so if we divide both sides by 3 times 10 to the 19th, divide by 3 times 10 to the 19th, then the wavelength is 1 times 10 to the negative 11 meters. So we take this magnitude right here, and we go back to our reference sheet, and this time we are looking at an X-ray. The last example for that equation, what if you're asked for frequency? So in the other two examples, we were given frequency and asked for wavelength, but the equation is the same. Okay, we're just plugging in a different value. So we still have 3 times 10 to the 8th meters per second is the speed. This time we have 1 times 10 to the second, is the wavelength, and the V is what we're solving for. So if we divide both sides by 1 times 10 to the second, we will end up with 3 times 10 to the 6th. And this was asking for frequency, so our unit is hertz. I want to point out that this second part is easy to make a mistake. So with the other two examples, we were solving for wavelength, and then we used the magnitude, the 10 to the something, in order to figure out what it was. But in this question, we solved for frequency, which is not on your reference sheet. Your reference sheet is in meters only, so that means that either way, no matter what you're given in the question, you still have to use wavelength to identify the radiation. So even though we solved and we did some math, okay, the wavelength was the number that was already given to us in the problem. So 10 to the second, if we go back to the reference sheet and look at that, 10 to the second is a radio wave. Okay, the other way that you would know that 10 to the 6th didn't work is the spectrum does not go that far. So if you're trying to find a magnitude that's not on the reference sheet, chances are you're looking at the wrong number, and you need to go back and look again and make sure that you have wavelength. The second conceptual understanding that we need to have about electromagnetic radiation is the connection between energy and frequency. So as the wavelengths shrink, okay, the frequency increases. And we already know, because we associate these words with negative things, that gamma rays are very intense, X-rays are very intense, ultraviolet rays are very intense, but we kind of know visible isn't. Okay, there's no danger to visible light. Infrared is just warmth. Okay, radio waves moving around us all the time. Microwaves, we have a negative connotation with them, but look at, here they are nestled in between two things that don't really negatively affect us. So what's happening here is as the frequency is increasing, the radiation is becoming more and more and more dangerous. That is because it is becoming more energetic. So energy increases with an increase in frequency to the point where it could even possibly mutate DNA. Okay, we know ultraviolet can burn skin and cause skin cancer. We know X-rays, we have to limit how many times we get those every year because we don't want to damage our cells. And gamma rays is the really nasty stuff that we associate with nuclear activity, causing a lot of mutation. So if we're comparing three and we're looking for the one with the lowest amount of energy, what we're really looking for is which one has the lowest frequency. So what you have to remember is your reference sheet only has wavelength on it. So if we're looking for low frequency, that means we're looking for large waves. So if visible light is here and gamma rays are here and microwaves are here, these are the biggest waves, which means they have the lowest frequency, which means they have the lowest energy. So two technical terms that we use to talk about light are the words photon, which really just means light. Okay, we're just talking about a piece of light. And then the word quantum, which is just a specific word for the amount of energy carried by a photon. So this image right here shows you 3 photons of colored light. If you were asked to compare them, the red photon has the largest wavelength, which means it would have the smallest quantum of energy because it has the lowest frequency. The blue wave, the blue photon, has the highest frequency because it has the smallest waves, which means it would have the highest quantum of energy. So just for fun facts to associate this with your regular everyday life, throughout most of the season, leaves reflect green light. Okay, but in the fall, they switch to reflecting red, orange, and yellow. Okay, that is because green has more energy. So when the trees are making a last-ditch effort to kind of eat a lot of sunlight, they want to absorb that high-quality green light instead of the low-quality red light because they get more power for every photon if they absorb green. So the chloroplasts go through a chemical change where they start absorbing green light and start reflecting red light because red light is kind of like the fast food of light. The waves are really big, and so that means that the photons have a very small quantum of energy. We can calculate the amount of energy carried by a photon using this equation. So energy is in joules, and we're talking about really, really small pieces of light. So the amount of energy per photon, the constant that keeps the frequency and the energy compared, is a very, very small number. And then we're going to plug in the frequency, since that is the part of electromagnetic radiation that most directly relates to energy. So if we're asked to calculate with energy, okay, we set up this equation where we have how much energy equals the constant, okay, which is always the same number, times the frequency, 3 times 10 to the 20th. And instead of having to divide, these are already set up so that you multiply to get your final answer. And the answer to this would be that this photon carries 1.99 times 10 to the negative 13th, and the unit for energy is joules. If we're solving this question, now we're looking for frequency, which is the V, and you're given energy, which is the E. So 1.99 times 10 to the negative 26 joules. Okay, we know that there's this much energy per frequency, negative 34. So we're going to solve for V by dividing. And if we round, our answer is 3 times 10 to the 7th, and the unit for frequency is hertz.